Matrix Methods for Linear Systems, and in this video we will be reviewing matrices and vectors. So a matrix is a rectangular array of numbers arranged in rows and columns. So we have m rows and n columns. And we call this an m by n matrix. The element in the ith row and the jth column. So if we look for that, we could use this element right here, and this element right here is in the second row and the third column. So this is A sub I j, where I is equal to 2 and j is equal to 3. We also use notation for that element like that for matrix A. Okay, we do have some special interest matrices. The first would be a square matrix, and that is when the number of rows equal the number of columns. And of course this is a 3 by 3, so of course you can see that I equals j. Okay, we also have what we call a diagonal matrix, and these are square matrices and I should have put a square matrix here. Of course, it's a 3 by 3. And we have a diagonal matrix. And I just forgot a O there. And with a diagonal matrix, it is a square matrix with 0 entries. Off of the main diagonal. And you can see those right here. And then of course this is our diagonal. The last special interest matrix we'll talk about is what we call a vector. And a vector is an n by 1 matrix. So it can have many rows, but only one column. Okay. The algebra of matrices is pretty straightforward. So basically for addition, we perform addition in the corresponding elements. So as you can see here, we will add 1 plus 1 to equal 2. We will add 3 plus 1 to equal 4, and so on and so forth. We also have where we multiply a matrix by a scalar. And it's pretty straightforward as well. Here, every element is multiplied by the scalar. So we have 3 times 1 and we have 3. Let me give you another example. We have 3 times 5 and we have 15. You can see right here that we have multiplied every element in the matrix by that scalar. Let's work our first example. So we have matrix A defined as this 2 by 3 matrix, and matrix B also is a 2 by 3. So we will first find A plus B, and of course we will add 2 plus 1, 0 minus 1, 5 plus 2, 2 plus 0, 1 plus 3, 1 minus 2, and we come up with matrix shown here. Now, in fact, maybe I will move this over here. And now let's go ahead and take a look at a matrix multiplied by a scalar. So here we have 7 multiplied by matrix A minus 4 multiplied by matrix B. So here we will have 14, 0, 35, 14, 7, and 7. And we will also multiply every entry by 4. And now we can add those matrices together, just adding each element to the corresponding, and we are subtracting each to the corresponding element. Okay, let's go ahead and take a look at the properties of matrix addition and scalar multiplication. Our usual algebraic properties hold. And you can take a look at them here. Basically, they're just pretty straightforward. And then we have properties of matrix addition and scalar multiplication. So let's talk about scalar multiplication. So we have, actually, this should be just matrix multiplication. So the product of two matrices A and B is formed by taking the array of the dot products of the rows of the first factor, and I've got them here in blue, with the columns of the second factor B. It might be a little bit confusing because I was just using this example, but basically for this entry right here, we will use the first row and the second column, and we will multiply 2 times 1 to come up with the 2. We will add that to 0 times negative 1 and come up with 0. And 1 times 1 is 1. And we will add those up. And that entire value, which ends up to be 3, is the result of those dot products of the ith row of A with the jth column of B. Okay, so I'm going to highlight that. The dot product of the ith row of A with the jth column of B. and that goes in the ijth entry. Okay, so the properties of matrix multiplication, and as you can see, we have the associative, distributive properties evident here. Order does matter. And now let's talk about a system. A, our coefficient matrix. And then X is the vector of unknowns. And then B is the vector of constants. So here we have that AX is equal to B. Call this matrix notation. Now we do want to make note that if B is equal to 0, the system AX equals B is said to be homogeneous. So that is if B is equal to 0. Let's go ahead and try an example and try some matrix multiplication and one of our properties. We'll begin with matrix A, B, and C, and they are all 2 by 2 matrices. So we're going to go ahead and multiply A by B. And as you can see, for this entry right here, we will write 1 times 1 plus -2 times 1. And so there we will have, and we'll just go ahead and write that as 1 minus 2. Let's do the same for the second column on the first row. So there we will have this column multiplied by this row, and we will have 0 minus 2. And we'll do the same here. Here we'll have 2 minus 3, and then this row and this column, we will have 0 minus 3. And we come up with that product as this matrix, -1, -2, -1, -3. Now, let's go ahead and find AC, that product. And we will do the same thing. And we come up with that product as -5, -1. -8, -1. Now, by the distributive property, we do have for part C that A multiplied by B plus C is equal to AB plus AC. And we just found AB and AC. So we will just add corresponding elements. And we end up with this matrix. Okay, let's talk about the transpose of A. So what would be the transpose of matrix A? So the matrix obtained by interchanging its rows and columns is called the transpose of A. And it's actually denoted by A with a capital T as a superscript. So as you can see, here we had a 2 by 3, and now we have a 3 by 2 matrix. And we just took this row and we have this column. Okay, a matrix identity. There is a multiplicative identity in matrix algebra, and it's called a square diagonal matrix I, and you can see it right here. That's our square diagonal matrix. And can see we have ones going down that main diagonal. So multiplying I on the right or left by any other matrix reproduces the previous matrix. So as you can see here, if you would call this matrix A and you multiplied I times matrix A, your result would be matrix A. And as you can see here, we have matrix A multiplied by the identity matrix. And again, we have that equal to matrix A. How about the inverse of a matrix? Some square matrices A can be paired with other square matrices B, having the property where B times A, now they are both square matrices, is equal to that identity matrix. So when this happens, it's pretty cool. When this happens, it can be shown that B is the unique matrix satisfying BA equals I, and also B satisfies AB equals I. So in such a case, if we have that case, B is the inverse of A, and we write that like this. Let's also talk about a singular matrix. We do need to keep in mind that not every matrix possesses an inverse. The zero matrix, for example, can never satisfy this equation. So a matrix that has no inverse is said to be singular. Now, if we know an inverse for the coefficient matrix A in a system of linear equations AX equals B, the solution can be calculated directly by computing A inverse B as the following derivation shows. And so AX equal B implies A inverse multiplied by A times X is equal to A inverse multiplied by B, and that implies X equals A inverse B. Now, the inverse of a 2 by 2 matrix, it is pretty convenient to have an expression for the inverse of a generic 2 by 2 matrix. And this is very easily verified. You can just take a look at it and see, but it's pretty nice. So we have AD minus BC minus BC. And we put that in that denominator, and then we find product of that with the entries shown here. So you can see D here, A, and then we have the opposite of B. So we do cross those diagonals, but we have the opposites in the other entries. Let's give a couple of these a try. We're going to compute the inverse of this matrix. We're going to form matrix A I. So let's go ahead and then we will then row reduce to matrix IA inverse shown like that. So let's go ahead and first write our matrix AI. So we have this matrix, and now we will perform row operations, and we will first divide the first row by 2 and then add it to the second row. So let's go ahead and multiply. So we're going to have row 1 divided by 2, and then we're going to have row 2 plus row 1 divided by 2, and that's going to be our new row 2. So let's go ahead and do that. So now row 1 divided by 2. And now we're going to add that to row 2. Okay, so now we're going to multiply the second row by 2/9. Let's do that first. And now let's take half of that result. So now we're going to take half of the new R2, and we will have row 1 minus 1/9 of R2, and that will be our new row 1. So now we'll have 1, 0, 4/9 and negative 1/9. So our answer is 4/9, 1/9, negative 1/9, 2/9. So this is the inverse of matrix A. Now, let's try this method. I'm going to put a little star by this. This is a convenient way to find the inverse of a 2x2 matrix. So let's take a double star and let's try this. Okay, so now we will have the inverse of this matrix is equal to, and then let's multiply 2 times 4 minus 1 times negative 1, and then we're going to multiply that, and remember we're going to have 4 here and 2 here, and now we're going to have a negative 1 and a 1 here. And so if we do that, we have 1/9 of our matrix here to the right, and of course we end up with the same result as we found here. Okay, let's go ahead and find the inverse of this 3x3 matrix. Now we can see where we had this formula. Well, actually, this goes into a statement further down in the lesson where we have these statements right here about not every matrix possessing an inverse. And it's a little bit further down here. And so basically we state here that let A be an n by n matrix, so we have a square matrix, and all of these statements are equivalent. A is singular, our matrix doesn't have an inverse. The determinant of the matrix is 0, which we haven't gone over yet in review. Ax equal to 0 has non-trivial solutions, and the columns or rows of A form a linearly dependent set. So there's a couple of ways we can do this, but I do want to show you this also. But if we go ahead and take a look here at this problem, we can see that if we use cofactor expansion, about the first row, and we are getting ready to talk about the determinant, we would say that the determinant, so again, we haven't talked about that yet, and I should have probably had this problem after that. But anyway, we have our cofactor expansion about this first row, and I will show you this. So we will take this determinant first, and then we will alternate with plus and minus, and now we're going to subtract this matrix. And then we will add, see if I can find one other color here. And I will be showing you how to find these determinants, but basically it's 2 times 2 minus 1 times 3. You can see that. So that's 4 minus 3, which is 1. And we'll do the same here. We're going to subtract 1 times 2 minus 1 times 2. And of course, that's going to be 0. And then we're going to add 1 times 3 minus 2 times 2. And of course, here we get 1. And so we are going to get this to be equal to 0. So by that theorem, and that is shown, I'll just go ahead and put a double star by that. Theorem 1. The inverse matrix does not exist. So this matrix does not have an inverse. Okay, let's find the matrix function x inverse of t. Before we do, let's go ahead and take a look. So for any t, we have that AD minus BC is equal to e to the t 4e to the 4t minus e to the 4t. So we're multiplying those diagonal entries, and we come up with 3e to the 5t, and that is not equal to 0. So we will be able to compute the inverse with that theorem, with that formula. And that was a formula for a 2 by 2 matrix. And let's go ahead and do that. So our inverse function is going to be equal to 1 divided by 3e to the 5t. All multiplied by, remember we will move these entries across the diagonal, and then these will have opposites on them. And now we will take each one of these entries and divide by 3e to the 5t. And we come up with 4/3 e to the negative t, negative 1/3 e to the negative t, negative 1/3 e to the negative. I think I made one little error here. That should be negative e to the t. Okay, so now we will have negative 1/3 e to the negative 4t, and then we will have 1/3 e to the negative 4t. And that is x inverse of t. Okay, let's go ahead and do that again with this 3/3. We're going to go ahead and use that method where we have our matrix, and here we have our function, and with the identity matrix on the right, and we will do our row operations. So let's go ahead and create that matrix. So let's go ahead and create that. So we have okay, so the first thing we're going to do is try to have our 0 entry in our second row. So what we will do is we will take row 1 and leave it. And so then we will have row 2 minus row 1, and that will be our new row 2. And then we will also have row 3 minus row 1, and that will be our new row 3. So let's go ahead and do that. So row 1 is going to remain. Now we're going to take row 2 minus row 1, and you can see we have a 0. For that first entry. And then we're going to have negative 2e to the negative t, and of course an e to the 2t. We end up with another 0 here and another 0 here. with row 3 minus row 1, and we have 3e to the 2t. And of course, doing those same operations, we will have row 3 minus row 1. So that's a -1, a 0, and a 1. Okay, so now let's go ahead and divide. Let's leave row 1 alone. And now let's go ahead and divide row 2 by a -2. And we will go ahead and make that our new row 2. So we'll just multiply row 2 by a -1/2. And then let's take row 3 and divide it by 3. And that will be our new row 3. And we'll see what we have here. Okay, so now we can go ahead and work on our row 1. So if we take row 1 minus row 3, that can be our new row 1. And then for row 2, we can take row 2 minus 1/2 of R3 and make that our new R2. And we are going to leave R3 alone. So let's take R1 minus R3. And you can see here that we will have e to the t, e to the -t, and 0. And now we have 4/3, 0, and a -1/3. And now let's take row 2 minus half of row 3 and make that our new row 2. And we will just rewrite row 3. Okay, we are going to take row 1 and subtract row 2 from it, and that's going to be our new row 1. So we're going to have row 1 minus row 2, and that's our new row 1. And that's about all we're going to do. We're going to leave row 2 and row 3 alone. And here we're going to have, we'll just copy these rows down. Whoops. We're going to subtract row 2 from that row, and that's going to be our new row 1. So now we're going to have e to the t, and here now we have our zeros, and you can see we have our 1, 1/2, and -1/2. And now row 2 and 3 are just going to be as they were previously. And I think I had, this should be a 1/6. Now with this last multiplication, you can see here that if I multiply row 1 by e to the negative t and make that my new row 1, and e to the t multiplied by row 2, and then e to the negative t multiplied by row 3. And so now you see we have the identity matrix on the left when we do that. And on our right, we have e to the negative t, and this is 1/2 e to the negative t, and we have negative 1/2 e to the negative t. And then for our second row, we have 1/3 e to the t, negative 1/2 e to the negative t. And actually, that's going to be e to the t. A little hard to see there. And then we have 1/6 e to the t. And our last row, negative 1/3 e to the negative 2t, 0, and 1/3 e to the negative 2t. Okay, so now you can see that this is equal to what we started with was x sub t I, and now this is I x sub t. I mean x inverse. So therefore, x inverse of t is equal to e to the negative t, 1/2 e to the negative t, negative 1/2 e to the negative t, 1/3 e to the t, negative 1/2 e to the t, and 1/6 e to the t, negative 1/3 e to the negative 2t, 0, and 1/3 e to the negative 2t. Okay, now let's revisit. We sort of talked about determinants in the previous problem, and as you can see, the determinant of a 2x2 matrix, and it's denoted DETA, determinant of A, or you'll see these two vertical lines on each side, just like we have here, and we will multiply across this diagonal and then subtract multiplying across that diagonal. And the higher order square matrices that are not 2x2, anything larger, we can define recursively in terms of lower order determinants. So these are determinants shown here. And so basically we form a sub-matrix when that entry is deleted. So if we are working on this entry, as you can see, we will delete this column and have this left as a determinant. Okay, and so the same thing would happen. I can change colors when we are working on this entry. We will delete this, and then we will have this as our determinant, and so on and so forth, okay? And you can do that with any row. You will pick a row and do that, okay? We will also talk about just revisit this again, that all four of these statements are equivalent. Let's just jump right to this determinant. And here we have, and let's go ahead and find the cofactor expansion about the first row. Okay, so it's going to be a cofactor expansion about this row here, 1, 4, 3, that first row. So what we're going to have is 1 multiplied by the matrix negative 1, 2, 5, 2. Remember, when we have it about this row, we will eliminate this, and this will be our determinant. Okay, and now we're going to subtract 4, and now we will eliminate that row, and we will have negative 1, 2, 4, 2, and then we will add 3 multiplied by negative 1, the determinant of that 2 by 2 matrix. And if we compute that, we will end up with negative 12 plus 40 minus 3, and we will end up with 25. And of course, how we came up with this is negative 2 minus 10. And this is 8 plus 2, which is 10, of course, times 4. And then here we have negative 5 plus 4 multiplied by a 3. Okay? And that's where we came up with that. Let's try this example. Determine the values of r for which the determinant a minus ri is equal to 0. So let's go ahead and first find the determinant of a minus ri, and that's going to be that's going to be 1 minus r, 1, negative 2, and 4 minus r. Maybe I should go ahead and put what ri is here. So that would be r multiplied by our identity matrix, and that's going to be r, 0, 0, r. So when we subtract that from a, that's where we come up with this. So the determinant of a minus ri. So let's go ahead and find a minus ri. So that would be 1 minus r, 1 minus 0, negative 2 minus 0, and 4 minus r. So we can see that that's what we are finding the determinant of here. Okay, so that's a matrix, but this is a determinant. So let's continue on. Here we will have 1 minus r multiplied by 4 minus r minus 1 multiplied by a negative 2. And we have 1 minus r multiplied by 4 minus r plus 2. And if we multiply that out, we end up with r squared minus 5r plus 6, and that is equal to r minus 2, r minus 3, and we have a quadratic equation. So r is equal to 2, and r is equal to 3. What about the calculus of matrices? A matrix A of T is said to be continuous at T naught if at every entry it's continuous at T naught. Moreover, A of t is differentiable at t naught if every A ij of t is differentiable at t naught. And how we write that derivative of A of t is like this, and we will take the derivative of every entry, and we will also define the integral like this. So we will take the integral of every entry. We do see our differentiation formulas for matrix functions quite obvious. The derivative of a constant matrix multiplied by the matrix is the constant multiplied by the derivative of the matrix, and so on. The derivative of the sum of the matrices is equal to the sum of the derivatives, and so forth. And you can see here the derivative here is the product rule. So those apply. Let's jump right in and find dx dt for this vector function. So we can say, and this should be dx, so we can say dx dt, dx of t dt is equal to the derivative with respect to t of this vector and of course we have the derivative of each individual, so we could go ahead just for this example and say it's the derivative with respect to t of each one of these functions. And of course, that leaves us with a vector that we have 3e to the 3t, 6e to the 3t, and negative 3e to the 3t. Okay, let's find dx dt for this given matrix function. Again, this is the derivative so this is dx dt of t, and of course we're going to just jump right in. This is 2 cosine 2t, negative 2 sine of 2t, negative 2e to the negative 2t. And now we have negative 2 cosine of 2t, negative 4 sine of 2t, and negative 6e to the negative 2t. And for our last row, we have 6 cosine of 2t, negative 2 sine of 2t, and negative 2e to the negative 2t. Let's take a look at this next example. Let's verify that the given vector function satisfies the differential equation. And you can see we have x prime is equal to this matrix multiplied by x. So differentiating x of t, you can see that we have 0 e to the t, negative 3 e to the t. So now, on the other hand, if we have this matrix multiplied by x, we have 0. So we're going to take this row and multiply it by this column multiplied by this, adding each entry together. So we could have 0 plus 0 plus 0. So we have 0 plus e to the t plus 0. And we have 0 plus 0 minus 3e to the t. And here we have 0 e to the t, negative 3e to the t. So these are both identical. Okay, verify that this given matrix function satisfies the differential equation. We'll do the same thing again. So now we have a matrix function. Its derivative, 2e to the 2t, 3e to the 3t, negative 2e to the 2t, and negative 6e to the 3t. I don't know why I wrote that. So close. Okay, and so now let's go ahead and find x prime, and that's equal to this 2 by 2 matrix multiplied by x of t. And here we have e to the 2t minus e, that should be a plus, e to the 2t. And then we have e to the 3t plus 2e to the 3t. And we have 2e to the 2t minus 4e to the 2t, and 2e to the 3t minus 8e to the 3t. And that leaves us with 2e to the 2t, negative 2e to the 2t, 3e to the 3t, and a negative 6e to the 3t. And these are the same. And that concludes this video.